Now that we have some intuition for orthogonal matrices when the size is equal to 2, let's look at the case where the size is 3. So, we're working in R3. We have the standard inner product in R3. A is going to be a 3 by 3 orthogonal matrix. So A satisfies the following equivalent conditions. First, A is an isometry, which just means A preserves the standard inner product. So if I take V and W, I apply A, take the inner product, that's the same as if we just took the inner product of V and W. Now, we could translate this to the equations AA transpose equals A transpose A equals the identity matrix. So that means the inverse of A is equal to A transpose. Finally, if we translate A transpose A equal to the identity matrix, that just says the columns of A form an orthonormal basis of R3. So if the columns are given by U1, U2, and U3, then the length squared of each column is equal to 1. And if I take the inner product of Ui with Uj, where I is not equal to j, we get 0. Now, in this talk, we want to give an interpretation in terms of geometry. So in the 2 by 2 case, two things could happen for an orthogonal matrix. If the determinant was equal to 1, then we were just looking at a rotation in the plane. If the determinant was equal to -1, we were looking at a reflection through some line through the origin in the plane. If we interpret the effect of A on R3, as we do in the 2 by 2 case, then we're going to take our standard basis, so E1, E2, and E3. Under A, our basis is carried to another orthonormal basis. So the determinant of A is equal to 1. Then I'm going to use my right hand, so we go from here to something like this. If the determinant of A is equal to -1, we're going to use our left hand. So we go from here to something like this. Now, we can be more descriptive than that if we think in terms of similar matrices. So our result is going to be, there's going to be an orthogonal matrix P. So the columns of our P are going to form an orthonormal basis of R3, such that P puts A in the form of a matrix like this. So we're going to have two blocks on the diagonal. Okay, our first block we could think of as corresponding to a rotation. Then in this block we'll have plus or minus 1. Now, what's happening here? So if we take a look at what the effect of A is on V3, so our third column, we're going to have that V3 is an eigenvector for A with eigenvalue plus or minus 1. So that means the line in the direction of V3 through the origin is mapped to itself by A. If the eigenvalue is equal to 1, that's going to be a fixed line, and that's going to be our axis of rotation. So the idea is going to be, we fix our line through V3, I'll call that L, and then in the perpendicular plane, which we call L perp, we're just going to rotate by our angle theta. If we have a -1 here, more or less the same idea. So for our line L, instead of being fixed pointwise, it's just going to flip through the origin, and then we're going to take the perpendicular plane and then just rotate by theta again. So that's going to be the description of all orthogonal 3 by 3 matrices in terms of geometry. Now, the first item we look for, the fixed line L. So I'm looking for a non-zero eigenvector with eigenvalue plus or minus 1. So first let's narrow down the possibilities of eigenvalues. So if I have a non-zero eigenvector V for eigenvalue equal to C, okay, C is real, then we have the equation A times V equals C times V. So if we take the inner product of AV with itself, by the isometry property, we can remove the A's. So that's equal to the inner product of V with itself, which is non-zero because V is non-zero. Now by the eigenvector property, we have the inner product of CV with itself. We can bring the C's out to get C squared times the inner product of V with itself. Then if I divide through by the inner product, okay, it's non-zero. We have c squared equals 1, or c is equal to plus or minus 1. So if we have any real eigenvalues for A, we have to narrow them down to one of these possibilities. Now, the question is, do we have to have a real eigenvalue? The answer is yes. So that's our proposition. There exists at least one real eigenvalue, and then since there is one, we've just seen that it has to be equal to plus or minus 1. Now, this is just proof by picture. So if we consider the characteristic polynomial of A, okay, the eigenvalues are going to be the zeros of the characteristic polynomial. Since I have a 3 by 3 matrix, the lead term on our characteristic polynomial is going to be lambda cubed. So the graph in the lambda y plane is going to be a cubic. Now, for a cubic that leads with lambda cubed, okay, what happens? The end behavior is, as lambda goes off to plus infinity, the y value goes to plus infinity. As lambda goes to minus infinity, the y value goes to minus infinity. Our polynomial is continuous, so if we connect the ends, we have to cross the lambda axis somewhere. So that means we have a 0 for the polynomial. That means we have at least one real eigenvalue. Now, that means we have a non-zero eigenvector. So on a form or fixed line L as the span, okay, and we'll call that non-zero eigenvector V3. We'll choose V3 to be a unit vector, and for now we'll just say AV3 equals CV3, where C is equal to plus or minus 1. Now that we have our fixed line, let's consider the orthogonal complement to our line. So L perp. Now, that's defined as, okay, we're going to take all W in R3 such that the inner product of W with V3 is equal to 0. So W and V3 are perpendicular, then W is perpendicular to any multiple of V3, so it's perpendicular to the whole line. So it's enough just to check against our V3. Proposition, L perp is invariant under A. What invariant means? If I take any vector in L perp, then A is going to carry that vector back into L perp. So invariant just means we're going to take our subspace, apply A, and then that subspace just maps back to itself. So invariant is the condition that we want if I want to restrict A to some subspace. Now, let's see that this condition holds. So if we take any W in L perp, that just means W inner product with V3 is equal to 0. So we want to show that AW inner product with V3 is also equal to 0. So we just follow our nose with the definitions. Now, first move we can make, I'll take A and put it in the second slot as A transpose. Since A is orthogonal, A transpose equals A inverse. Then in a second, we'll see that A inverse on V3 is just equal to C times V3. Since I could pull the C out, we have W inner product with V3, and then by definition of L perp, that's equal to 0. So AW is going to land back in L perp. Now, to see this last step, this is just a little bit of manipulation. If I have AV3 equal to CV3, where C is equal to plus or minus 1, we'll multiply both sides by C inverse, A inverse. So it's just going to switch the C and the A and put an inverse on each item. So that means A inverse V3 equals C inverse V3, but since C is equal to plus or minus 1, C inverse is equal to C. So that's what I need for this step, and that gives me that L perp is invariant. How do we make use of invariance? Well, we have A carries L perp to L perp. So we'll choose any orthonormal basis V1 and V2 of L perp. That'll give us an orthonormal basis of R3, V1, V2, and V3. So we'll load these vectors in as the columns of an orthogonal matrix P. Now we consider P transpose AP. So if I consider the effect of A on each of our basis vectors, okay, so A on V3 is just going to go to C V3. So the columns tell us how to set up the linear combination of A and our vector. So I'm going to have 0v1, 0v2 plus cv3. For v1, all we know is that A carries v1 back into L perp. So we have coefficient v1, coefficient v2, and 0v3. Similarly for v2. So from invariance, we get block diagonal form. Now, next step I leave as an exercise. So just by using manipulation and the facts that P and A are orthogonal matrices, show that P transpose AP times, this matrix times its transpose is the identity matrix. Now, if we apply this relation to the matrix on the right, that'll give that B transpose is the 2 by 2 identity matrix. So that means B is orthogonal also. Using the results from part 1 on 2 by 2 orthogonal matrices, we can describe B precisely. So if the determinant of B is equal to 1, B is a rotation, and we can write B in the form cosine theta minus sine theta cosine theta. If we want to find theta, the eigenvalues will occur in a complex conjugate pair, e to the plus minus I theta. Now, with this B, our matrix here occurs in the form on our first board, so we have our result in this case. If the determinant of B is equal to -1, then B is a reflection, and B can be put in the form cosine theta minus cosine theta. Here, the eigenvalues are plus minus 1, so A will have all real eigenvalues, plus minus 1 and C. If we perform another orthogonal change of basis, we can put A in the form 1, 1 minus 1, or minus 1 minus 1, 1. So both of these matrices are in the form on our first board, so again we get our result in this case. Now, the only loose end here, you would need to show that 2 orthogonal change of bases give us another orthogonal change of basis, but that's straightforward. With our result, we can give a recipe for C and theta in terms of the matrix A. So, A can be put in this form. By similarity, these matrices have the same determinant and trace. So the determinant of A is equal to C, which is plus or minus 1. The trace of A, that's equal to the sum of the diagonal entries, is 2 cosine theta plus C. Now, when we find a theta that solves the second equation, we'll also have minus theta as a solution. So if theta is not a multiple of pi, we have 2 solutions plus minus theta. If I insist on keeping our angles between 0 and 2 pi, I want to pick the angle that's between 0 and pi. The way I do that, we'll take our form here, and then we're just going to take a look at the angle that comes out. So the idea is I could switch between theta and minus theta by switching the order of v1 and v2. So if you recalculate the linear combinations that correspond to the columns, when I switch v1 and v2, it's going to move this minus sign down to here. Then we can use the evenness and oddness of cosine and sine to push the minus signs to the inside to give us a block like this. Now, let's look at an example. So I'll have A in this form. Okay, note A is orthogonal since the columns form an orthonormal basis. Determinant of A is going to be 1, which is our C. We take the trace of A, okay, the sum of the diagonal entries, we get this expression, and that's equal to 2 cosine theta plus 1. So I solve for cosine theta, I get minus 0.973. If we take the inverse cosine of minus 0.973, we get 2.91 radians, or 166.7 degrees. So geometrically, we're going to have a line that's fixed pointwise, our axis of rotation. We're going to take the corresponding perpendicular plane and rotate by 166.7 degrees. Now, if I want a better picture, we'll need to go find our V1, V2, and V3.